Newton's rings is an example of interference in thin films of non-uniform thickness. Here in this Newton's rings experiment, we will take a plano convex lens which is kept on a plane glass. So in this case, what is happening at the center? Plano convex lens is touching the plane glass plates and its thickness T is becoming 0. As we move away from the center, its thickness is gradually increasing. Whereas in the interference in films, the thickness T is always going to remain constant. So that's why Newton's rings are also a special case of interference in thin films of non-uniform thickness. So let us try to understand the experimental arrangement to obtain Newton's rings. So what are the apparatus required? So to perform the Newton's rings experiment, the apparatus required: one, traveling microscope, right? First one is what we required is traveling microscope. Second one, sodium vapor lamp, sodium vapor lamp, or we will call it as monochromatic source. Third one, Newton's rings set. These two things, plano convex lens and plane glass lens, put together, we will call it as Newton's rings set. And the most important thing is 45 degrees angular, and the last one is black color paper or cloth. So these are the apparatus required to perform the Newton's rings experiment. So in this case, what we are going to have is a source. So light is moving in all possible directions in a spherical form from the source. By keeping a double convex lens, we will collimate this light. So this is the propagation direction of light. And we kept our Newton's ring set. We kept our Newton's ring set at this position. This is our plano convex lens, and which is kept on a plane glass plates. But you can see here the light is traveling parallel to the Newton's ring set, but we need the focusing of this light onto this Newton's ring set. For this purpose, what we are doing is we are keeping a glass plate at an inclination of 45 degrees. 45 degrees angle. So what is happening is angle of incidence is going to become 45 degrees, and angle of reflection is also going to become 45 degrees. Total it is undergoing 90 degrees reflection, and now this light is falling on Newton's rings set. And the light from the upper surface of this glass plate and lower surface of this glass plate will undergo interference, and we are going to form concentric bright and dark Newton's rings. Bright and dark Newton's rings are going to form. These rings can be observed through our microscope. This is the incident angle, and this is the reflection angle, and the interference pattern we could able to see through our microscope kept over this Newton's set. So this is the experimental arrangement for performing Newton's rings experiment. Question 1, what we want to answer here is why the Newton's rings are circular in shape. So if you see this Newton's ring set, only one point of contact where the thickness of air film is 0 and around 360 degrees we have air surrounding it. So the simple reason why we are getting circular fringes in Newton's rings is due to circular air wedge. Okay, so due to circular air wedge we are able to get these circular rings only. Coming to the second thing, I told you Newton's ring is also similar to the concept of thin films. So let us try to understand how it is going to have the phenomenon of interference in these Newton's rings. So this is plano convex lens, and this is our plane glass plate. So let me show you first of all oblique incidence. Later we will discuss about normal incidence. Normal incidence. So what is happening here is now a ray of light is falling with an oblique incidence of I. And again, what is happening? It is moving from air to glass, undergoing some bending, diffraction. So from upper surface of this mirror, it will undergo reflection and we will get R1. From lower surface, from denser medium to rarer medium, from glass to air, it is moving like this, and it is undergoing reflection from here, and it is emerging parallel to the ray. So same as the case in our thin films. In thin films also, we told you that amplitude division is taking place and we are getting R1 and R2, and we identified the total path difference. Here also it is A, this point is A, this point is B, this point is C, and this is of the normal line, this is D, and when we divide this into two perpendicular triangles E, so the discussion already we have taken in thin interference in thin films. So what is that path difference we got is 2 mu t cos r plus lambda by 2. So this is the result what we get earlierly in our interference in thin films discussion. So the same thing is taking place in the case of Newton's rings also. Path difference is equal to Newton's r plus lambda by 2. But coming to this Newton's rings, light is falling normal to the Newton's rings. So that's why we'll call it as normal incidence. So the same kind of phenomena taking place here, but the angle between the incident ray and reflected ray is 0 degrees, and the medium that is present between these two glass plates is air, whose refractive index is mu is equal to 1. So in this path difference case, we are going to substitute these two conditions. What are the two conditions? R is equal to 0 degrees and mu is equal to 1. So what happens? Path difference is equal to 2 into instead of mu 1 t cos 0 degrees plus lambda by 2. So the path difference in the case of normal incidence is 2t plus lambda by 2, right? So the path difference what we are going to get in the case of Newton's ring is path difference is equal to 2 plus lambda by 2. So let us find out the conditions for Newton's rings. So earlierly in the case of thin films we have only two conditions, constructive condition and destructive condition. But coming to this Newton's ring case 1, where we are going to get this, what is it called? Touching point. Plane glass plate is touching the plane of convex lens. So what is happening here? At the center, case 1, at the center. What is the value of t? T is equal to 0. Substituting t is equal to 0 at this point. So what happens to path difference? Path difference is equal to 2 into 0 plus lambda by 2. So the path difference condition will become equivalent to lambda by 2. And path difference, so we told that the condition for constructive interference is path difference should be equivalent to L lambda, but it is becoming different from L lambda. So path difference is equivalent to lambda by 2 is a condition for destruction. So always at the center of Newton's rings we will get a black spot. So why the central spot of Newton ring is always dark? The reason is this one. So at t is equal to 0, path difference condition is becoming equivalent to lambda by 2, which is a condition for destruction. So always at the center of Newton's rings we will get a black spot. This is case 1. And coming to the case 2. What is the case 2? Condition for constructive interference. Condition for constructive interference. So what is that condition? Natural general condition is path difference is equal to N lambda. So what is our path difference? 2t plus lambda by 2. So 2t plus lambda by 2 is equal to N lambda, which means 2t is equal to 2n minus 1 into lambda by 2. Okay, 2t is equal to plus N lambda, so 2t is equal to N lambda minus lambda by 2. So it is becoming 2n minus 1 into lambda by 2. It is a condition for construction. And the case 3, condition, comparing the condition of destruction, condition for destructive interference. What is the condition for destructive interference? Path difference is equal to 2n plus 1 into lambda by 2. So comparing with this, 2t plus lambda by 2 is equal to 2n plus 1 into lambda by 2, or it means 2t plus lambda by 2 is equal to 2n lambda by 2 plus lambda by 2. So 2t is equal to 2n lambda by 2 plus lambda by 2 minus lambda by 2. So 2t is equal to n lambda is the condition for destruction. So this is about the how the experimental arrangement of Newton's rings. We have to describe in our own words the experimental setup and how we perform the obtain the Newton's rings. Then the 3 conditions, case 1, case 2 and case 3.